Hello again. This is the Pencrest High School AP Physics C video series. This is video 1G, vector multiplication. What we're going to see is that there are two ways to multiply vectors. The first is called the dot product or the scalar product. The other is called cross product or the vector product. We'll do the dot product first. It does not produce a vector result. It produces a simple magnitude without any direction. Therefore, it does not have vector components. The cross product, we'll see, produces a vector result. So to illustrate the dot product, we'll say that we have a vector A and a vector B. Vector A is axi plus ayj plus azk, and vector B is bxi plus byj plus bzk. Of course, ax, ay, and az are the x, y, and z components of the vector A, and bx, by, bz are the components of vector B. Now the dot product, again, it's just a magnitude. It's defined as AB cosine theta. A and B are the magnitudes of each of the vectors, and theta is the angle between them. This is in red, or the box is in red, so you know that means it's on your formula sheet. The magnitudes of A and B, if you recall, the magnitude of vector A is ax squared plus ay squared plus az squared, and then take the square root. So we know how to do that. Now, if we don't know the angle between the vectors, we can derive a formula for the dot product this way. We're going to write out the two vectors, axi, ayj, azk, and then dotted with bxi, byj, bzk. We're going to FOIL those, expand all the terms, and what we find is that the coefficients we can just multiply. So here is ax bx, that's this term, times this term, and then dot the two vectors I dot I. So this is the first term we get from foiling. Then we have axi dotted with byj, that's this term, axby, and then I dot j, axbz, and then I dot k. And you can follow it the rest of the way. Looks like a big mess, but as we'll see, most of the terms are going to go away. Now, if we go back to the definition of the dot product, AB cosine theta, where the theta is the angle between them, we can realize that all of the unlike dot products go away, because the unit vectors are at right angles. The angle between them, therefore, is 90 degrees, and the cosine of 90 degrees is 0. We know that the definition of the unit vectors implies that they have a magnitude of 1. So effectively, what we see is that all of the like dot products go away. The unlike dot products go away. The like dot products, because the angle between them is 0, and when you dot a vector with itself, effectively you have a magnitude of 1 times 1 times 1, which is the cosine of 0. So we end up getting rid of all the unlike dot product terms, and we end up with this simplification: ax bx and then I dot I plus ay by j dot j plus az bz k dot k. These three dot products are just 1. So we can actually get rid of them, and we get a pretty simple formula. A dot b is ax bx plus ay by plus az bz. This is the easy one to remember. What I find people making the most mistakes here is they try to call these or this combined term an x component and a y component and a z component. Technically, they're not vector components. They're just magnitudes, so you can just add them up. Okay? Add them up and get a simple magnitude. Okay? Something that you probably want to commit to memory is that any unit vector that is dotted with itself is equal to 1. Any unit vector that's dotted with a different unit vector, the result is 0. Okay? Now for the cross product is a little more complicated. It's going to yield a vector result. So we'll take the same two vectors and we'll cross them. Again, the cross product is defined as A cross B equals AB sine theta. Again, A and B are the magnitudes of the vectors, and theta is the angle between them. The cross product creates a vector that is perpendicular to both of the original vectors, or perpendicular to the plane produced by the two original vectors. The value of AB sine theta is the magnitude of that resulting vector. Now, once again, if we don't know the angle between the vectors, we can derive a formula for the cross product. We're going to set it up the same way. Instead of a dot, we'll put a cross in between them. And again, we will FOIL all the terms. We'll expand them all. We get AX, BX, and then cross the two vectors, I cross I. And then again, all the way down the line, we end up with 9 different terms. Now again, it's a mess. Some of the terms will go away, but not as many as we saw in the dot product. And when we look at the expansion here, we'll see that the like cross products go away because there's an angle of 0 degrees between them and the sine of 0 is 0. So those 3 terms will go away, and we are left with the unlike cross products. So we have AXBY, and then I cross J, AXBZ, I cross K, AYBX, J cross I, etc. Again, we took these right from what was left from the original expansion. So now, to sort these out, I cross J, I cross K, J cross I, etc. We're going to consult the magic unit vector triangle, and you'll see it right here. And what we see here is that if we're finding the cross product of two unit vectors by moving around the triangle clockwise, so this way, the result is the positive of the remaining unit vector. So in other words, if we're doing I cross J, the result is K. If we're doing J cross K, the result is I. If we're doing K cross I, the result is J. Okay, so clockwise around, it's positive. If we're going to find the cross product of two unit vectors by moving around the triangle counterclockwise, then the result is the negative of the other unit vector. In other words, if we're going this way, I cross K is negative J, K cross J is negative I, J cross I is negative K. So again, clockwise positive, counterclockwise negative. We'll go back to the 6 terms we had left over with the unlike cross products, and we will replace each of the unlike cross products with the result from the magic triangle. So I cross J is K, I cross K is negative J, J cross I is negative K, and etc. So all of these get translated into their vector cross product result using the magic triangle. Now it just got a lot simpler because we can take the negative sign and move it out front. It's just multiplying by negative 1. We can move it out front and then combine the coefficients of each unit vector and write it as shown. So there's an I term here, and there's an I term here. And what we have is AYBZ minus AZBY, and then that's my X component. We combine the J terms. There's a positive J term here, AZBX, and then a negative J term here, AXBZ, times the unit vector J hat. And then the K terms, we have a positive K term here, AXBY, negative K term here, AYBX, times K hat. Now that is a reasonably complicated formula. It's the hard one to remember. But if you think about the pattern to each of the coefficients, there is a pattern for the I hat or the X direction. We have the other two coefficients, AY, BZ, and then you flip them, AZ, BY, and subtract. For the J term, again, we have the other two, Z and X, X and Z. For the K term, we have the other two, X and Y, Y and X. Switch them and subtract. One easy rule to remember is that any unit vector that's crossed with itself is 0. Any unit vector crossed with a different unit vector, you use the magic triangle. Okay, there is another way to go from a cross product to a result, particularly with I, J, and K. This is tough to put into words. We'll do this in class with your right hand. Align your right hand so that your pointer finger is in the direction of the first vector. That's A in this case. And when you bend your middle finger is in the direction of the second vector in the cross product. So that's B in the diagram here. You may need to contort your hand in a way that it's not supposed to do, but you'll find a way to manage. When the two fingers are aligned properly, A and B, so your pointer finger and your middle finger, then your thumb, when it's extended, will point in the direction of the resulting cross product. So we will demonstrate that in class with multiple cross products. There's another version of the right hand rule. If you point your straight right hand in the direction of the first vector A, and then curl your fingers or bend your wrist so that they point in the direction of the second vector in the cross product, again your thumb will point in the direction of the resulting cross product. Okay, so that's it for dot and cross products. We will use them multiple times throughout the year. So it's a good idea to take those two blue box formulas, or at the very least the methods to obtain them, and commit those to memory. All right, next up is Newton's laws. Until then, enjoy, and I'll see you again soon.